Okay, so in this problem, we have a north-south bridle path intersecting an east-west river at point O, which we'll call point O for the origin. It says at noon, a horse and a rider leave O traveling north at 12 kilometers per hour. At the same time, a boat is 25 kilometers per hour east of O, traveling west at 16 kilometers per hour. Express the distance between the horse and the boat as a function of the time after noon. So that's after they leave. Okay. All right, so let's draw a little picture here. Okay, so we're going to make, so the way they've described it, they're saying the bridle path intersects an east-west river at point O. So the river is represented by that horizontal axis there, and then the path is with the vertical axis, and then right here is O. Okay? All right, now the rider is going along the path, going at 12 kilometers per hour. So he's traveling north, so that means he's going this direction. Okay? And it says he's going 12 kilometers per hour, right? So that means for every hour he travels, that's an additional 12 kilometers, right? So we need to generalize the situation for any amount of time. So we're going to say his distance here that he travels is 12t. Right? If after 1 hour he would be 12 kilometers away, after 2 hours he would be 24 kilometers away, etc. Okay? All right, now it says at the same time the boat is 25 kilometers east of the origin. So east is to the right. Okay? He starts here 25 kilometers away, and he's traveling west, which means he's heading back towards the origin. Okay? Now, the distance that he travels is 16 kilometers per hour, so we can represent this with a 16t. Now, what would be the distance then between the origin and where the boat ends up? So what I mean by that is what is this distance right here going to be? How can we represent that?
25 minus 16.
Very good. If he starts 25 kilometers away and he's traveling at a rate of 16 kilometers per hour, or 16t, we can subtract the 16t from the 25 to give us that value there. Okay. All right, now we're ultimately after this distance between the rider and the boat, right? Now what did I just create there? I created a right triangle, yes? So I can say the distance squared, d squared, is equal to 12t squared plus 25 minus 16t squared. Okay, we're going to simplify all this out, expand it out. That would be 144t squared. And then if you square the binomial, you'll get 625 minus 800t plus 256t squared. And of course, we can combine those two together. And why don't I at the same time square root everything? So I'm going to end up with d equaling the square root of 400t squared minus 800t plus 625, and that would be kilometers. Okay. Then I think we can simplify that radical a little bit. There's a common factor there that I can pull out of 25, which is nice because that's a perfect square, right? So I pull that 25 out, I get 16t squared minus 32t plus 25 left. And then why don't I finish off with my final answer here, going to the function notation. The distance between the rider and the boat at any given time t would equal 5 times the square root of 16t squared minus 32t plus 25. There we go. Any questions there? All right, so always make sure you're looking to simplify at the end, right? Based on, the particular problem. All right, example 5. Okay, water's flowing into a conical tank with the vertex down. That's 100 centimeters wide, 250 centimeters deep at a rate of 40 cubic centimeters per second. All right, so the first thing we want to do is find the volume of the water in the tank as a function of the height of that water, okay? Find the volume of the water in the tank as a function of the height. All right, so let's do some labeling on our picture here. All right, we were told that the cone itself is 100 centimeters wide, and from top to bottom, 250 centimeters deep. Okay, does anybody recall the formula for volume of a cone? Volume of a cone? It's not one we probably have memorized, is it? Okay, well, it's an expression or a function in terms of both the radius and the height. 1/3 pi r squared h. Okay, now where does that come from? If you're just looking at a cylinder, okay, the formula for that, you would be taking the base times the height, okay, which would be pi r squared would be the base, and then the height would be h, right? Now that this is a cone, we need to end up taking 1/3 of that, okay? All right, so it says express the volume within the tank as a function of just h of the water. Okay, so we need to be able to express the radius here in terms of h. Okay. All right, so it says here, if we're 100 centimeters wide, what is the radius of the tank then? This is 50. Okay, and then we don't know exactly how much water is in there yet. So where the top of the water is, I'm just going to call the radius of that r right now. Okay. And right there is our height. And I also need the height of the water itself. Okay, so what I've created here are two triangles that are similar to each other. Let's extrapolate it. Okay, so the larger triangle we know has a base of 50. The smaller triangle, base of r. Larger triangle, that distance there we know is 250. And then the smaller triangle we'll just call a value of h. Okay, so similar triangles are proportional to each other, right? So I can say h over r is equal to 250 over 50. And that simplifies nicely. H over r is equal to 5. Or h equals 5r. Or you could say r equals h over 5. And that's ultimately how we want to look at this. So we're going to take that h over 5 and we're going to substitute it in right there. And that's going to allow me to switch my notation to v expressed solely as a function of h. That'll equal 1/3 times pi times the radius, which is now h over 5 squared, times another h. And then we're going to simplify. And let's call that pi over 75 times h cubed. There we go. All right, so now that the volume is expressed in terms of the height, it says represent h as a function of the time t that the water's been flowing into the empty tank. Okay, so you go back to the original problem. We've already used this 100 centimeters. That led us to our radius. We've used the 250 centimeters. That led us to a height. What we haven't used yet is this rate of 40 cubic centimeters per second, right? Okay, so think what that means. At time 1, the volume that's in the tank in terms of the water would be 40 times 1, 40 cubic centimeters. At time 2, we would be at 80 cubic centimeters. Well, let's generalize it. At time t, the volume would be at 40t, right? Okay, so take your function from the previous answer, and you're going to replace v of h with 40t then. And notice we want to represent h as a function of time. So that means we need to solve for h. We need to isolate h here. Okay, and this one's kind of involved. So first thing I'm going to do is multiply both sides by 75. Those will eliminate the fraction. You'll get 300t here, or 3000t I should say, equals pi times h cubed. You're going to divide the pi over. And you're going to take the cube root of both sides. And let's reverse everything. I'm going to say h equals the cube root of 3000t over pi. Okay, now I can simplify that a little bit. 3000 is 3 times 1000, right? 1000, isn't that a perfect cube? Okay, what is the cube root of 1000? 10. So this would be 10 cube root of 3t divided by the cube root of pi. Are we simplified fully yet? If this were a test, would you say that's complete simplified answer, circle it, go on to the next problem? I hope not. What do we still need to do? Yeah, we don't like those radicals in the denominator. That's an irrational denominator, right? Okay, so we're going to rationalize. I'm going to multiply the top and the bottom by the cube root of pi squared. Because it's a cube root, not a square root, right? Pi times pi squared would create pi cubed. And what's the cube root of pi cubed? Pi. So let's call this 3 pi squared t all over pi. There we go. Now we're simplified. Okay, and for good measure, let's tack on. We should put our units on there. This is the height of any given time value, so it should have units of centimeters. Okay. Questions there? All right, one more. Bear with me here. Okay, find the point on x minus 3y equals 5 that's closest to the origin. All right, so let's try to visualize this. That's a linear equation in standard form. Those are easy to graph if you find intercepts. Okay, so if I make x 0, negative 3y would equal 5. That would mean y is negative 5/3. And if I make y 0, that means x would be 5. Okay, so let's plot those. I don't need it to be like a super accurate drawing. Just more or less, we just want to visualize. Okay, so we're trying to find a point on this line that's closest to the origin. So right here, let's pick a different color. Right there's, of course, the origin, 0, 0. And then somewhere roughly over here, we've got some point on the line, which right now I'm just going to designate xy, generic xy, where this distance between them would be as small as I possibly can make it, right? Okay, so I'm going to use the distance formula. I'm going to find the distance between point P and the origin there. Okay? Now we know our distance formula, general, square root of x2 minus x1 squared plus y2 minus y1 squared, right? Well, in this case, our points are x, y, and 0, 0 that we're plugging in. So I'm going to make it easy on myself. I'm going to make x2 just the x value. x1 is 0. And then y2 would be y. y1 would be 0. That's going to simplify to the square root of x squared plus y squared, yes? Okay, so currently that is a function in terms of both x and y. Okay, what I'm going to do is try to get it in terms of a single variable, either x or y, okay? So go back and look at the original linear equation, x minus 3y equals 5. Would you rather solve that for x or would you rather solve that for y? I hope you said x. Just add 3y over. If I solve it the other way, if I solve it for y, I'll end up with a fraction, right? I don't want to mess with fractions if I can avoid it. Okay, so I'm going to take this 3y plus 5, and I'm going to substitute it in down here. So now the distance will be expressed solely in terms of the y value of my point. The square root of 3y plus 5 raised to the second power plus y squared. I'm going to simplify that. So that's what, 9y squared plus 30y plus 25 plus the other y squared, or 10y squared plus 30y plus 25. Good so far? Okay, now we're to a point because we now are in terms of one variable here where we can answer the question, right? It says find the point that is closest to the origin. Okay, so that means we need the smallest distance possible, right? The smallest distance possible. Okay, well, for this square root to produce the smallest distance possible, I need the radicand to be as small as possible, right? So we're going to ask this question. When is 10y squared plus 30y plus 25 smallest? Well, that's a quadratic expression, right? And it opens upward if we were to graph the parabola associated with it, right? Okay, so where would we be smallest at? At its vertex, right? At its vertex. Okay, so we're going to get that vertex with a y equals negative b over 2a. That would be negative 30 over 2 times 10. That's negative 3 halves. So the y-coordinate of this point is negative 3 halves. To get the x-coordinate, use the original linear function. That's 5 minus 9 halves, which isn't that just 1 half? So the point 1 half, negative 3 halves, is closest to the origin on this particular line. How about that?